Okay, good evening all. Right, so let's continue with our discussion on information system security. So last class we finished symmetric key cryptography, and also we started asymmetric key cryptography as well. So today we want to finish asymmetric key cryptography and do some past papers as well. Okay, so that means we've completely finished the topics. Okay, so there won't be any separate past paper discussions at the end for information system topic. Okay. Right. So let's finish this topic today. Uh, that is asymmetric key cryptography. Okay. So then we have small topics. So now we are doing the big topics. Okay. So these topics are small topics. Okay. And from today's topic, you get most number of questions. Actually, today's topic and previous week's topic. Okay. So actually, after today's topic, more than half of your paper is covered. And so let me open the note. Right. Asymmetric key cryptography. We have started the topic, so we just need to pick from where we stopped. So remember, in symmetric key cryptography, we use the same key for both encryption and decryption, which is more efficient, simple, but there's a big issue that is basically you uh, share your secret with the other party. So therefore, the same key that we use for decryption is used for encryption, which is so unless you trust your sender, it's not going to work like your head office and branch, or something like few. But when you work with general public, like Facebook, a bank, Gmail, or any other e-commerce application and so on, we must rely on public key cryptography because then our key is with us private. We only share the public key. So using the public key, you can encrypt, but you can't decrypt. So decryption can be done by only with the private key with this receiver. And remember, we can use the other side, uh, changing the who generate the keys. If key pair is generated by the sender, we can do it for use it for signing. We discuss both. Okay. So encryption, decryption, where the keys are generated by receiver. Digital signing, which is for authentication, whereas the encryption, decryption is for uh, confidentiality. So now you must be really familiar with these words, right? Authentication, confidentiality, right? So private key, public key. So that is why we call it asymmetric key cryptography. See, not symmetric, two different keys. Okay. So in encryption, decryption, the sender get the public key or anyone get the public key. So sender can encrypt, but even sender can't decrypt. Okay. So this is how encryption, decryption happens. So receiver generate the two keys. Public key is given to encryption process. Private key is kept secret and used by the receiver to decrypt. So these are related keys. So okay, and these are special encryption decryption algorithms. Okay, so when plain text is encrypted by the public key, only this private key can decrypt it, which is kept as a secret configured in your server. These are configured in Gmail server, Facebook servers, and so on. So we all encrypt using the same public key. Actually, our browser, if you go to your browser, you can see what is your public key for the Facebook. So it's same for you and me, but they only change it time to time. Okay, time to time. So digital signing, same concept, but this time the keys are generated by sender because the purpose is not encryption. Purpose is signing, authentication. So you get the digest of your original content and sign that digest using the private key. So then your public key is available for anyone who want to verify whether it's coming from you. So the receiver can get the public key of sender and check whether is it really coming from the sender. Because when it is signed by the private key, it is only verified. It is verified only when it is signed by the secret key. No one else knows it. Okay. So any questions about these things? Because this is where we stopped. Okay. And remember, we can combine these two together. That is, both sender and receiver has key pairs. Sender get the public key of the receiver and encrypt it, and then sign it using the private key of the sender, and then send it to the right. So then send it to the receiver. So receiver first decrypt it using his or her public private key. Now it is in plain text. Now the receiver can verify using the public key of the sender. Okay. Public key of A. If you call sender A, receiver B. So you can't change it, right? It's not encrypt and sign. It's sign and encrypt. If okay. Here decrypt and verify. Right. So related concepts. So this is where we stopped, right? So from where this is where we are going to start. So we are not going to learn exact algorithms of public key cryptography. We are going to discuss actually some concepts related to algorithms and a bit of a scaled down version of the algorithm, simplified version of the algorithm. Because these algorithms are so complicated, we are not going to look at the exact algorithm. We are just going to look at simplified versions or related concepts of the algorithm. So that is where we have these subtopics. Trapdoor function, discrete algorithms, relative prime numbers, Euclidean GCD algorithm, primality test. So you get separate questions also, like that almost every year there's a question on Euclidean GCD algorithm. So these are not public key cryptographic algorithm. These are concepts related to public key cryptography. Okay. Discrete logarithms, trapdoor functions, relative prime numbers, primality test, all these. Some of these are very complicated concepts as well, but we are only looking at uh, reasonably simple concepts only. Okay. And also most of the time at theoretical level, sometimes we do some calculations as well. Right. So one such concept is trapdoor function. Trapdoor function. So what is a trapdoor function? This is something we used in public key cryptography like RSA algorithms. So trapdoor function is a function that is easy to compute in one direction, but difficult to compute in the other direction without some additional information. So that is exactly what we want to do. Okay. So that additional information is in encryption decryption, that additional information is with the receiver. So therefore receiver can decrypt it easily. Others, for others, it's a big, it's complicated problem, right? Complex problem. But if you have that additional information or the private key, it's a simple problem. So that is called, that kind of functions are called trapdoor functions without additional information, difficult to guess. With that information, it's straightforward task to get the value. So another name for trapdoor functions is one-way function. Okay. One direction easy, other direction difficult. Okay. So these are the characteristic of trapdoor functions. So one-way functionality. So in one direction, computation is easy. Other direction means inverse function. Right? It is a complex task. So that should be one of the feature of trapdoor functions. We use trapdoor functions in public key cryptographic algorithms. So you can see fx is x to y is easy. But y to x, that is f inverse y or f inverse x, inverse function is hard to compute. Unless you know the trapdoor, or unless you have that key, secret private key. Okay. So that is one-way functionality. Forward, easy, backward, difficult. So what is meant by the second feature is trapdoor knowledge. So if you want to efficiently calculate this return task, you need some additional knowledge, additional piece of information. So with that information, it's efficient. Without that information, it's hard. You can see without that additional information, hard. With that additional information, that is your private key basically, it's easy, efficient. So it's one way, but other way is possible if you have that additional piece of information. It's not impossible, but without that additional information, it's near impossible. So that is the second feature. And obviously, this is asymmetric. So that is why asymmetric means, for example, samamitical. So this is symmetric, but this is asymmetric. Okay, asymmetric. So the way we do the encryption is not the way we do the decryption. That is not simply reverse. No, it's not simply the reverse algorithm. It's a different algorithm, but related, but you need that additional information to do that. That is called your private key in encryption decryption. Okay. So what are the three features of trapdoor function? One-way functionality, trapdoor knowledge, asymmetric. Right. So the second related concept is discrete logarithm. So we all know that logarithm is the inverse of exponent. Exponent. So that is something you all know, right, from O level, and we also discuss logarithms and exponents in semester one maths also. So we know that 2 to the power 10 is 1024. That is exponent. So what is the reverse process? Log to the base 2 2024 is 10. So this is the reverse. This is, if this is fx, this is f inverse x. And you know that finding 2 to the power 10 is easy. Right? Anyone can say, right? What is 5 to the power 3? 5 into 5 into 5, 125. What is 10 to the power 3,000? What is 6 to the power 2? 36. But this is also not impossible, but somewhat difficult than this. What is log 2024? So then you must find something. Which power of 2 is 1024? Yes, it's 2 to the power 10. So therefore log 2024 is 10. I'm not saying it is impossible, but it's more challenging than logarithm. Finding log is more challenging than finding the exponent. But things get even difficult when you go for modular logarithm or discrete logarithm. So now we have right? So modular arithmetic was there in semester one sometimes back, but now they have removed it, right? About 2 years ago, they removed. So therefore, you didn't get modular arithmetic, but with your previous batch, actually, you are the guys who didn't get the modular arithmetic. Uh, I think you had the modular arithmetic, right? In semester one, but now they have removed it. So it's like 100 mod 10 is zero because when thousand is divided by 10, the remainder is zero. Say 1002 mod 10 is 2. So therefore, if you include mod also, things getting more difficult. So this process is difficult compare relatively. But when we include mod also like mod 8, especially mod prime numbers, finding the logarithm find, become much even more difficult. That is just make the problem even harder. So while calculating exponent is relatively easy, finding the logarithm is harder. And it becomes harder when we introduce modular arithmetic also. So that is another concept we use in uh, asymmetric key cryptography. So just you need to aware, right? Yes, we use trapdoor function. We use some algorithms use discrete logarithm. Okay. So this is an example. Don't worry about this. They are not going to ask about calculations because anyway, semester one also now they have removed uh, modular arithmetic. So this is just an example for you to get a feeling of rather than for exams. So for example, if someone says what is x if it is 8 in mod 11, this is not very easy to find. Of course, you can find it. If someone asks what is 2 to the power x 8, you can straight away say it's 3, right? But this is 2 to the power x equal 8 mod 11. Okay. So that means 2 to the power 3 is 8. Mod 11 means again 8. Okay. Because 8 is less than 11. So then you know that x is 3. But if it is bigger than 11, then you need to divide by 11 and get the remainder. So that make it even more challenging. So the idea is make it challenging. Make it challenging. And not impossible, but make it challenging, especially when the numbers are big. Okay. And these are just part and partial of that, right? Just nuts and bolts of the algorithms. So that these algorithms, asymmetric key cryptographic algorithms, especially RSA algorithms, heavily depends on prime numbers. Clever use of prime numbers. So now we have discussed how many concepts? Trapdoor function and its three features. Discrete algorithm, sorry, discrete logarithm, the use of prime numbers. So if someone talk about this, we talk about pretty much asymmetric cryptographic algorithms. So you know what is a prime number is. Prime numbers are numbers divisible only by itself and 1. And remember, there are infinite number of prime numbers. So don't think that after sometimes we run out of prime numbers. No. Right? So your common sense, gut feeling might say, okay, after sometimes there won't be any prime numbers. But in reality, it's a funny thing also. You can keep looking for prime numbers. Actually, people still looking for bigger prime numbers. I think last prime number was found about 3, 4 years ago. And a lot of computing power is required. So there are people, universities that are still looking for even bigger prime numbers. So what is the biggest prime number so far? Okay, I can't say that is the biggest prime number so far discovered. Right. So you can see it was so you can see it's a big number. So this is the value 2 to the power this minus 1. It has this number of digits, right? So that is 41 million digits, and it was discovered in last year 2024. Okay, as part of this project. So that means still we are looking for bigger and bigger prime numbers. So why we are interested in? Actually, there's a prize winning also. If someone find a bigger prime number, then he or that particular organization or university get a prize uh, winning also. Okay. So why we are interested in these big prime numbers? Big prime numbers are very crucial part of cryptography, especially asymmetric key cryptography. Okay, especially RSA algorithm. So then what is mean by relative prime numbers? Relative prime number means prime number is a number like 30, 11, 17. So relative prime number means two numbers can be either relatively prime or not relatively prime. Okay. For example, 8 and 15. Those are relatively prime. 8 is not a prime number. 15 is not a prime number because 8 is divisible by 2, 15 is divisible by 3. But 8 and 15 are relatively prime. So that means those two numbers are divisible. Both numbers are divisible only by 1. There's no common factor to both other than 1. For example, 8 is divisible by 2 and 4, but not divisible. 15 is divisible by 2 and 4. 15 is divisible by 3 and 5, but not 8 divisible by 3 and 5. So there are no common factors other than 1. So therefore, yes, 8 and 15 are both composite numbers or non-prime numbers, but 8 and 15 are relatively prime numbers. Okay. So same similar here, 9 and 25 are relatively prime numbers. So in some algorithms, we don't use the concept of prime numbers, we use the concept of relatively prime numbers. Now, how many concepts? Trapdoor function, okay, discrete logarithm, prime numbers, relatively prime numbers. Okay. For example, are these two relatively prime numbers? 12 and okay, let's say 21 and 28. Can someone tell me, are these relatively prime numbers? Yes or no? Simple answer. So relatively prime, if no other than one, no number will divide both these. No, why? So then if you say those are not relatively prime, you need to give a reason. Why do we say that these are not relative? Or why do you say? So if someone says not relatively prime, you need to give a reason. Relatively prime, you don't need to give a reason because if you say relatively prime, that means no common factor. But if you say not relatively prime, so then you must say what is the common factor, right? Because both numbers are divisible by 7. Yes, both numbers are divisible by 7. So that means these two are not relatively prime. Okay. Right. So this is another concept related to prime numbers or numbers. That is, any number you can factorize until you get prime numbers. So that is called prime factorization. Prathamaka sadhaka. So any number you can keep factorizing until you get all prime numbers. Then of course, since prime numbers doesn't have factors, you need to stop it. So that is the ultimate you can do. You can't go beyond that. Okay. So you know how to do that, right? For example, if it is 24, you start with smallest number. Anyway, we did this kind of things in semester 1 maths. Say 2 into 12. Now 2 is prime, you stop it. But now again check whether the smallest number is 2. Yes, 2 into 6. 2 to the power 2, again 6, 2 is there. And now 2 is a prime number, 3 is a prime number. So we have found the relative, we have found the prime factors. So there's no further factorization. Fine. So I hope you can remember those things, okay? Because you get mathematical questions. When we do past papers today itself, you will find that kind of questions. So the next thing is another concept that we used in asymmetric key cryptography is the concept of GCD. Again, we have discussed this in semester 1 maths, right? Fundamentals of maths. So GCD, greatest common divisor, that is the biggest number that divides the given numbers. Biggest number. There, you are looking for the biggest. But that number must divide all the given numbers. So you can see 24 is divisible by 6, 18 is divisible by 6. There's no bigger number than 6 that divides both 24 and 8. For example, if you take 9, 18 is divisible by 9 but not 24. If you take 12, 24 is divisible by 12 but not 18. So therefore, GCD of 24 and 18 is 6. For small numbers, you can just use your common sense and find it. But for big numbers, you need a systematic approach. We discussed one approach in semester 1, right? You find the prime factors and you take only common factors, right? Remember we discussed? So for example, say if you want to find relative GCD of this factorized 56, 2 into 28, 2 into 2 into 14, 2 to the power 2 into 2 into 7, 2 to the power 3 into 7. So then take 24, smallest 2 into 12, 2 into 2 into 6, 2 to the power 2 into 2 into 3. Now we have the 5 factors. Now what we do? If it is common only we take. Okay. And we take the higher index. So 2 is common. There's no higher index, both are 3. So therefore you need to take this into. Do we have any other common? No, 3 is not common, 7 is not common. So then that's it. If you have any other common things, again you need to take, but you need to take the smaller index, okay? But here there's nothing for small index because both are 3. Therefore, nothing to multiply. So that is 8. So that is how you get it. Okay. But that is one approach. But this approach take little bit more time because you need to find prime factors. Especially remember we are looking at very big numbers, trillions, trillions of trillions. Those are the type of numbers we work with cryptographic algorithms. So then finding these is not impossible, but take a lot of time. Okay. So therefore we have another algorithm to find GCD. Okay. So this approach we have already discussed. Okay. So this is your uh, grade 4, grade 5 approach. Oh, we discussed that in semester 1 also. Right. Find the prime factors and take only common factors and lower index, lowest index and multiply. There's nothing called lowest here. It's just 2 to the power 3. Right. This is another example. So 2 is common, the lower index is 1. 3 is common, the lower index is 1. 7 is not common. So therefore, GCD is 6, 3 into 2. Right. in the exams, you are not supposed to use this approach, because in the exams they give you sometimes two or three numbers and ask you to find GCD. Sometimes the examiner will specifically ask you to use Euclidean GCD algorithm, or examiner will not tell anything. But even though examiner is not specific, make sure you don't use this approach. Your expectation is how to use Euclidean GCD algorithm. So this is different approach, but it gives you the uh, GCD much faster for big numbers, very big numbers. Okay, so this is the definition. In recent years, they have not asked the definition, but about 6, 7 years ago, I have seen some past paper question asked, write down the Euclidean GCD algorithm. So therefore, if you can remember, you better remember this statement. This is what Euclidean GCD algorithm says. Don't try to understand, just remember, because marks. Okay. So what? How do you say? If x divides a and b, right? If x divides a and b, x also divides a minus k to the power b for every k. A and b is here. Okay. For example, say if your x is uh, say 3, 3 divides 9 and 12. Right. So then it says 3 also divides a minus, that is 9 minus k is integer, say 5 times b 12. Negative number, but it's going to be divided by 3 also. Okay. So that is what is right. If x divides a and b, x also divides a minus k into b. So if there's a question asking you to write down the Euclidean algorithm of GCD, this is the statement you need to write. Right? So you better remember it if possible. But most of the time, almost every year, there's a question on finding GCD. Rather than they ask you to write the algorithm. So it is easy. Right? So let's take an example. There's a systematic approach. It really useful when you're looking at GCDs of big numbers. How to do that? Take the bigger number, whatever the bigger number. In this case, bigger number is 1030. We want to find the GCD of 1030 and 960. That means the biggest number that divides both 960 and 1030. So take the bigger number and write it as a multiple of the smaller number. So that is 960 into 1, because there's only one 960 within 1030. So then 960 into 1 plus remained 70, because 960 plus 70 is 1030. So that is your step number 1. Then take this number and write it as multiple of this. How many 70s are there for 960? So it's 30. And then 50 remains, because 17 to 13, 910. So then 40 remains, because 960 minus 900, sorry, 50 remains. 960 minus 910 is 50. So that is your second step. So the third step is you write 70 as multiple of 50. And of course, it's just 1, then 20 remains. So then you take 50 as multiple of 20. 20 into 2 is 40, 10 remains. So then write 20 as multiple of 10. That is exactly 2. When you get 0 here, you stop. You need to keep doing this until you get 0 here. Okay. So remember, 1030 is the GCD of 960 and 70. 960 is the GCD of 70 and 50. 70 is the GCD of 50 and 20 and so on. Okay. Actually, it doesn't mean that 70 is the GCD of 50 and 20, but 70 is related to the GCD of 50 and 20. Okay. And therefore, finally, when you get 0 here, your answer is this one. Right? When you get 0, your answer is here. Okay. So almost every year there's a question like this. Shall we do a past paper question and come back? Right. Find this greatest common divisor of 5460, and this is 2024 last year paper, is equal to 140. You need to say true or false and justify. This is how you get some questions. Right, quickly do it. You don't get calculators. Take 2 minutes and do it. So take the bigger number and write it as multiple of smaller number plus the remainder. The bigger number is 5460. That is 1 times 3220 plus this minus this, 0 minus 0, 0, 6 minus 2, 4, 4 minus 2, 2, 5 minus 3, 2. That is your step number 1. So then you write this as multiple of this, and you keep doing this until you get 0 here. Anyone got the answer? You need to do it fast. Anyway, you get plenty of time for these papers. Usually time is not an issue. Right, so now you can write 2240 as 2 times 980 plus that is 0 1960, 2240, 0 8 by 280, right? So then I can write 980 as how many 280s? 3? No. Yeah. 0 840. 980 minus 840 is 0 40, right? So then 280 is 40 into what? 7 plus 0, right? So then we got 0, that means your answer is 40. Right? Answer is 40. Anyone got 40? So you can't just say true or false. You need to justify. Okay, otherwise you don't get any marks. Right. Oh, is it 140? Ah, yes. Ah, no, right. How can 140? So I got it up to 280, correct? 200 is 2 into 140. Ah, yes. 280 is no, right? Ah, this is not 40, 140, right? That is why I miss it. That is why I miss it. This must be 140. Yes, 9 minus 8 is 1. Yes, yes. That is why I made a mistake, right? 8 minus 4 is 4. 9 minus 8 is 1 is 140. So therefore 280 is 140 into 2 plus 0. So therefore final answer is 140. Yes, 140. I made a mistake in the last step. Right. So the GCD of 5460 and 3220 is 140. So therefore answer is true. Okay. Let's see whether there's another question. Right. So this is another question. This you should be able to do it. You start with 8,468 is, sorry, 12,468 is this into 1 plus remainder. So then this next one. After sometimes you will get 0. When you get 0, this is your answer. So therefore, this one's GCD is actually 4. You can say, though these are very big numbers, the GCD, the biggest number that divides both these numbers is 4. So Euclidean algorithm, very quickly you can find it because you get 0 here, right? So that you should be able to do it by yourself. Okay, so that is, you can see 2023 paper, 2024 there was a question. Let's say with the 2022 is also there's a question. Yes, 2022 also, every year there's a question. GCD algorithm. Right. So remember, examiner has not mentioned what to use. So this must be the right. But easier thing is use, and that is the expectation. You use GCD algorithm. 300 is how many? 18, blah, 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 blah. Okay. And you will get the answer as 6. Okay. Right. So you can see all 3 years, last 3 years, there's a GCD question. Okay. That means Euclidean algorithm question. Right. So now we have discussed another concept, that is GCD. Now remember, these are concepts related to asymmetric key cryptographic algorithms. Actually, what we are doing is, in reality, right, just like that philosophers and right elephants, right, we are just looking at different parts of the algorithm rather than looking at the algorithm. We just try to understand bits and bolts of the algorithm, right, rather than looking at the real algorithm. Right. So therefore, this is another nut and bolt related to asymmetric key cryptography, that is use of GCD. Earlier we discussed prime numbers, relative prime numbers. Okay. Right. So another concept is primality testing. Right. Primality testing. So sometimes, as I told you, we need to find big prime numbers or prime number relatively prime with another big prime number. Okay. So there are different techniques to find it fast. find it fast. So one such approach is called probability testing, right? Sorry, one of the primary testing approach is trial division. So these are called probability testing, different algorithms. So one such algorithm is trial division. Actually, this is the easiest algorithm, right? So this approach says this is called trial division. Divide n by all integers up to root 10. If you want to check whether particular number is prime number, say you want to check whether 29 is a prime number, right? Say you are not very sure whether 29 is a prime number. Actually, 29 is a prime number. Let's assume you are not very sure. So this is how you do it in trial division approach. Find the root of 29 roughly. You don't need to find exact value. For example, it is 5 into 5 to the power 2 is 25. 6 to the power 2 is 36. So therefore, this is between 25 and 36. So therefore, this must be 5 point something. Okay, 5 point something. So your task is check whether 29 is divisible by any prime number smaller than 5.3. Any prime number, whole numbers. So what are the smaller than 5.3 prime numbers? 2, 3, 5. If 29 is divisible by 2, it's not a prime number. If 29 is divisible by 3, it's not a prime number. If 29 is divisible by 5, it is not a prime number. If so, if 29 is not divisible by any prime number smaller than this number, this is a prime number. Okay, this is a prime number. Is it clear? Okay. For example, you want to find out whether 61 is it a prime number. Now find roughly the square root of 61. Right? For example, 7 to the power 2 is 49. It's bigger than 61. 8 to the power 2 is 64. So therefore, this must be 7 point something. That means you need to check whether 61 is divisible by any prime number smaller than 7. Right? 2, 3, 5, 7. If 61 is divisible by any of these prime numbers, it is not. This is not a prime number. If not, this is a prime number. Okay. So that is called trial division. And different mathematicians later found some more algorithms to check the prime number or check whether number is a prime number. So these are some other concepts, other techniques, but we are not going into details because those are very complicated calculations. Okay, you can see these are very complex calculations, but just remember these names. So another primary testing is Solvay and Strassen approach. Just if you see these things, because sometimes they ask true or false. So if there's a statement saying that okay, this is a primary testing, you need to say yes, true. Okay. So another one is Jacobi function. So these are some more primary testing techniques, but we are not going into details because those are fairly complicated approaches. But these approaches give you make that test faster. Make that test faster. Check the prime, whether it's prime number or not, much faster. Remember, we talk about 30, 40, right? Digit prime numbers. Right. So now we move on to now we have discussed some features, so some concepts used in public key cryptographic algorithms, so see asymmetric key cryptographic algorithms. Now we can move on to the real algorithms. The real algorithms. Okay. So the first one is actually we are going to look at few algorithms. What are those algorithms? RSA algorithm, ecliptic curve algorithm, ECC, digital signature algorithm. Actually, these are the three algorithms we are going to use. We are going to discuss. So this is not a public key cryptographic algorithm, but this is mentioned in your UCSC note. Therefore, I took it, right? So these are related to more key exchange protocols. So therefore, don't think that these are public key cryptographic algorithms. These are not. These three are public key cryptographic algorithms. This one we are going to look at in our next topic, that is key exchange, because the fail one is key exchange algorithm. Okay, right. So we'll take a small break. After the break, we'll move on to our cryptographic algorithm, starting from RSA algorithm. Okay, right. So now time is 7:55. We'll start at 8:10, and we'll continue with our estimate. Now, so far we discussed is some concepts. Now we are into the real algorithms. Okay, but real algorithms also we are looking at that scale down versions. Okay, right. We'll start at 8:10. Okay, so let's continue. Right, so now we move on to the real algorithms. Actually, these are also not the real algorithms, the scaled down versions, but we are looking at the real algorithm. Okay. Right, so the first one we are looking at is, remember we are going to look at three algorithms: RSA, elliptic curve, digital signature algorithm. Okay. Right, so the first one is RSA algorithm. So RSA stand for the three guys who came up with this algorithm, the Ron Rivers, Adi Shamir, and Adelman. Okay, so they are the three letters coming from their names, RSA. Uh, so they developed this somewhere around 1978, and this is the most widely used asymmetric key cryptography algorithm even today. Okay, so this is based on some concepts like factorizing large integers, prime numbers, and so on. Okay, and we can use it for both encryption and digital signing. So there are some algorithms we can't use. You can use only for encryption, decryption. Some algorithms only for digital signing, but this can be used for both. Okay, so that is advantage. So this is how the RSA algorithm work. Uh, so this is a scaled down or simplified formula. You need to remember this because every year, sometimes not one question, two questions from RSA algorithm. So this is super, super important for your exam. Okay, super, super important for your exam. So this is a scale down function, not the real function. If you have plain text, P, let's take it as a number because at the end it's a binary number anyway. Uh, it is P, the ciphertext value is, encrypted value is P to the power E mod n. Mod means when you divide by n, the remainder. Okay. And then the ciphertext is sent to the receiver. The receiver can decrypt it using this formula. So remember your input is ciphertext now because you have calculated the ciphertext from plain text. That is C to the power D mod n. Okay. So these values, so therefore this calculation, of course, C is ciphertext, P is plain text. So therefore that is our related to our data. So then there are some other numbers, E, N, and D. So these numbers are generated by receiver. Receiver. We remember in encryption, decryption, the keys are generated by receiver. Out of these, D is kept private. D is kept private, and E and N are public. Why? We are giving E and N for encryption. If we are giving something to the sender, then those are public. So therefore, E and N are part of the public key. And here also we use N, but D we have not shared. But ND is not private key because N we have shared. But D we have not shared, but D is used in our decryption algorithm. So therefore, D is the private key. So this is something you need to remember. So you need to remember the formulas. And what are the formulas? C equal, let me write it somewhere because we are going to do some past paper questions also. C equal P to the power E mod n. Uh, reverse process is P equal C to the power D mod n. Okay. So that is how it is done. Okay, that is how it is done. So you need to remember these two formulas. Okay. And you must know that D is your private key. Uh, E and N are public, part of the public key. Okay. Right. So therefore, your private key is D. right? Your private key is D. So this is your private key. Okay, right. So how do you find these D, E, and N values? So there's a specific approach. So this is something again you need to understand. Okay, right. So this is how you do it. Choose two large prime numbers P and Q. Remember, P and Q are not, so this P and Q is different from plain text. Okay, so here P means plain text. C means hypertext, but this is different P and Q. Okay, so this is how you start it. You select two large prime numbers P and Q. Okay, very large prime numbers. So that is why I told you that we are keep looking for new bigger prime numbers. And then when you multiply, so these remember, so your N is P into Q. P and Q are big prime numbers. So you need to select P and Q. So something like, say, let's not go for a very big prime number because we can remember something like 13 and 41. So then you need to calculate phi, which is P minus 1 into Q minus 1. That means if your prime numbers are 13 and 17, this is 13 minus 1, 12 into 17 minus 1, 16. So then you need to select a large integer e, it's not prime number, integer e, which is relatively prime to your phi, that is 12 into 16. Okay. And it must be bigger than, so e must be lesser than 5. It must be something between 1 and 5, a large integer. Right. So now you have found e also. Ne. So then you need to find d. So how do you find d? Select d such that e into d mod 5 equal 1. So that is how you find d. So then you have found d also. So remember d is your private key. E and n are public keys. Part of the public key. Okay. So then c is p to the power e mod n. P is c to the power d mod n. Okay. Fine. So that is how it is calculated. Right. So you get every year, most of the time, two questions from this. Okay. Right. So C is P to the power E mod 10. P is, that is decryption, C to the power D mod 10. And D is your private key. So that is when you do encryption, decryption. So remember, digital signing is a reverse process of encryption, decryption. Okay, reverse process. So in encryption, decryption, keys are generated by receiver. But in encryption, decryption, keys are generated by sender because sender sign it. So therefore, now the formula is reversed. Your sign text is P to the power D mod 10. Okay. Of course, these letters can be changed by yourself, right? Because these are just terms. So therefore, in digital signing, C is P to the power D mod 10. So remember, uh, D is your private key. D is your private key. And verification is P equals C to the power E mod 10. So this red one is for encryption, decryption. Black formula is for signing and verification. Actually, the black formula, so this formula is same as this. Rather than C, I use P. Okay. So this black formula is same as this. So rather than P, I use C, C to the power E mod 10. So in black formula, keys are generated by this side. That is signing. In encryption, decryption, keys are generated by red side or the receiver. Okay. Is it clear? Right. We'll do a question. Right? So you don't get this kind of a questions, right? But you never know. Sometimes you might get this kind of question also when the examiner is fed up with asking the same type of questions. Okay. So this is just an example. So remember, first we start with two prime numbers, big prime numbers, right? So let's say those two prime numbers are 11 and 13, but in reality, those are much bigger than this. But for ease of our calculation, let's take 5 and 11 and 30. So then you multiply. So that is your n. Remember, n is there in our formula. N, right? So that is 11 into 30. Now we have found n, in this case 143. Now you need to find phi such that it is p minus 1 into q minus 1, in this case 10 into 12. Sorry, p is 11, 11 minus 1 is 10 into 12, 13 minus 1 is 12, that is 10 into 12, 120. Phi is not part of the key, it's just intermediary value. Then you need to select a large integer e relatively prime to 5, relatively prime to 120, and it must be between 1 and that value. So you can find any number which is relatively prime 120. Okay. So here we have taken it as 11 because 11 is relatively prime to 120. So why do we say 11 is relatively prime to 120? Because there's no number divide both these numbers other than 1. Now you need to find d such that e to the power e into d mod phi is 1. That of course you need to do a bit of guessing. So then you will find that something like 11 work because 11 into 11 mod 120 because our phi is 120 is 1 because 11 into 11 is 121, 121 mod 120 is 1. So therefore now we have found d also. We have found d, e and n. So that means we are done. Now if you are going to do the encryption decryption, your C is p to the power e mod n because we know n, d, and e, and p is c to the power d mod n. Now you can see that you can't randomly select e, n, and d. It doesn't work, right? So don't think that you can use any value for e, d, and n. You need to find your e, d, and n in this logic. So if you use select e, d, and n using this logic, it's going to work. So that means you have generated a key pair, private public key pair, because private key consists of D and N. Public key consists of E and N for encryption, decryption. Okay. Right. So let's do an exercise. Right. So this is actually past paper question. Right. Past paper question. Right. Kamal has RSA public key E equal 11, N equal 91, and RSA private key this. Nimal has public key this and private key this. Assuming the role of Nimal and showing all steps clearly, encrypt and decrypt the message m equal 20 be sent to Kamal. Okay. So remember, it's going to be sent to Kamal. Who? Nimal. And this is not digital signing, this is encryption decryption. Right? This is encryption decryption question. So therefore, who generate the keys? Kamal. So therefore, you don't need this. Nimal has public key and public private key. That is unnecessary details for you. That examiners just to confuse you because if it is encryption decryption, the keys are generated by receiver. Receiver is Kamal. Okay, because it clearly says assuming the role of Nimal and showing all the step clearly encrypt and decryption message to be sent to Kamal. So Nimal to Kamal. So then keys are generated by Kamal. So Kamal has E equal 11, N equal 91. 91. Right? N equal 91. K E equal 11 and D equal 59. D equal 59. So remember, you need E and N here. E equal 11, N equal 91. For decryption, you need D and N. Right? You need D and N. This and this. For encryption, you need this and this. Right? So now the question is, if your message is 20, okay, so you need to explain what happened to what is your, now your plain text is 20. Then what is ciphertext and how it is getting decrypted. Okay, so let's do the encryption. So encryption is C equal P to the power E mod 10. So therefore my plain text is 20 because message is 20. 20 to the power 11 mod n is 91. Of course, for this one, you need a calculator. If you get this kind of a question, they will allow you to use calculator. You need to take your calculator at the exam hall, or actually at the admissions. They will mention whether you can use calculator or not. Okay, right. So then 20 to the power 11 mod 91. So I will use the calculator. Normal calculator is enough. Scientific calculator or even normal calculator. So I go for the scientific calculator. 20 to the power 11. 20 to power x to the power y 11. Right? So this value, you can see big number. Now mod 91. So mod function is there. Mod, again, අනුවකින් බෙදුවම ඉතුරු කීයද? අර ලොකු number එක. That is 41. So therefore, the ciphertext is 41. Right? Ciphertext is 41. So that means your plain text 20 is sent as 41. Your plain text is 20, but what you are sending is 41. Now you need to show that what happens in the receiver side. So the formula is P equal C to the power E mod n. So my ciphertext is 41. Okay, it's E to the power, E is 11. Mod n is 91. So that must be 20, if this is correct. Okay, let's see. 41 to the power 11. Of course, without calculator, you can't do this, right? How can you find 41 to the power 11? Right? 41 to the power 11. It is this. So then you need to find mod 91. Mod 91. If you get 420, it's correct. Yes, we get 20. So therefore, yes, so it works. So you just need to show that it is working. So you get 20. So therefore, the answer, this is what you're supposed to show. You need to do this calculation and show that yes, we are getting back 20. Okay. So just use the formula properly. But remember, don't use this because this is unnecessary details for you. Right? Because receiver is Kamal, you need to use Kamal's keys. So this entire thing is not needed. So you get 41 and then you get 20 back. 41 to the power 59, mod 91. Sorry, not 59, right? So your D is, yes, this must be not 41 to the power 11, 41 to the power 59, right? C to the power, no, C to the power E, right? Sorry, C to the power D. I made a mistake also. So this must be C to the power D, that is C to the power D, right? C to the power D. So therefore 41 to the power 59, right? Mod 91. Let's redo the calculation. 41 to the power 59. It's even bigger number. Mod 91. Yes, anyway, it's also 20. Right? It's also 20. So therefore, our answer is correct, but I made a mistake earlier because C to the power D. D is 59. Right? 41 to the power 59. Mod 91 is we are getting back the original plain text, right? Plain text. So examiner has given it as M, but I just take it as P. Is it clear? Is it clear? Okay. So that means you need to remember these formulas. Okay. Right. So this is another example. We have taken plain text as 19 and we have done the calculation again. So anyway, they have given the D and everything. Here we get ciphertext as 66. Again, we are doing the reverse calculation and we are getting back 19. So you start with 19, ends with 19. So remember these numbers must be selected using that logic. You can't just randomly select these three numbers. Then this formula is not going to give you the plain text back. Okay. Is it clear? Because most of the time there are two questions from RSA algorithm. Right. So this is a digital design question. Right. So in digital design question, you need to use this black formula, the reverse. So this formula is here, this formula is here, and the keys are generated by sender. Okay. Can you do this? Give it a try. Okay, because this is our first example, I will do it. So Nimal has this. Suppose Nimal generate the plain text M2 to be digitally signed. That means Nimal is going to sign it. Okay. Nimal is going to sign it. Okay, just give me 1 minute. I won't plug in my power adapter. Okay. Right. So now Nimal is going to do the signing. Nimal. Whoever the receiver is there, let's call it Kamal for the time being. So Nimal has the key, right? N equal. So now the formula is uh, P to the power D mod n. Mod n. Here the verification formula is C to the power E mod n. Let's call this C. Let's call it P. Actually, this is not ciphertext and plain text. Rather, this is basically uh, sign text and verification. Okay, but we just use C and we say that it is C and P as a convention. Right. So now you need to show that. Okay. So now how do you sign it? Uh, Now we have n equal 33. We need n and d equals 7. Other side we have uh, N and E. Public key is with the receiver now. Receiver need to verification. N equal 33, same. E equal 3. Now let's calculate. P to the power D mod n. P is M, message. That is 2 to the power 7 mod 33. Of course, this you can do without calculator also because 2 to the power 7 is easy. But I will be using the calculator to make it fast. 2 to the power 7. Sorry, I made a mistake. 2 to the power 7. 128 mod 33. That is you divided by 33. What is the remainder? Mod 33. That you don't need a calculator. That value is 29. So your ciphertext or the sign text is 29. Now you need to show that when you give 29 here, you get the original 2. Okay. So your ciphertext, so the sign text in this case is 29 to the power 3 is 3 mod n is 33. So now you need to calculate this and show 29 to the power 3. Again, I will be using calculator. Right. 29 to the power 3. Now you need to find mod 33. When you divide by 33, what is the remainder? The answer is 2. Yes, that should be 2, right? Correct. So it worked because we got the original value. Because we start with 2 and send 29, and to in the receiver side, it verified when the receiver tried to verify it, whether it is from this guy, it says 2, yes. So yes, it must be 2. So here we use it in reverse. So this formula is used for signing, and this formula is used for verification. So basically, this black formula is this red formula. This black formula is this red formula. Okay. Is it clear? Right. So this is also past paper question. Right. So now we'll move on to ecliptic curve cryptography. Right. ECC. Remember, this is the second formula. So the second approach. So the first algorithm is RSA. That is what we discussed so far. Now this one is elliptic curve cryptography. So this is very advanced mathematical approach, and actually ECC is better than RSA. Therefore, now ECC has pretty much replaced RSA. Actually, I forget to mention about that. I told you that RSA is the most widely used. Actually, not RSA. RSA is still widely used, but now ECC has become more popular than RSA because ECC is much stronger algorithm with smaller key size. You can get the same security as RSA. Okay, and again, just like RSA, we can use ECC to both encryption and signing. So this is very important because some algorithms you can only use for one task. So RSA you can use for both. ECC you can use for both as well. Okay, elliptic curve cryptography. So we are not going to look at the exact algorithm for ECC, but we are going to look at just a little bit of a overview of or the theory behind this because this is a heavily mathematical formula, mathematical algorithm. Okay. So elliptic curve is something like this. So this kind of a curves are called elliptic curves in maths. This is not ellipse. Ellipse is like this. This is related to ellipse, but not ellipse. So ellipse is something like this. This is circle, this is ellipse. And then you have hyperbola, parabola. Okay. But this is elliptic curve. Okay, elliptic curve. Uh, so don't worry, they are not going to ask about these formulas and so on. So just remember it's related to elliptic curve, right? And some algebraic concept of elliptic curve is used in this particular algorithm. Okay, elliptic curve cryptography algorithm or ECC. Earlier one is RSA, right? So it's the concept of elliptic curve is used in different fields, right? This is a mathematical concept. It's used in number theory, it's used in physics, and of course, it's used in cryptography. So what we are interested is the use of elliptic curve in cryptography. Okay, so the ECC asymmetric key algorithm. Remember, we are in the asymmetric key algorithms. Okay. And in your notes, they have given you some concepts related to elliptic curves like point addition, point multiplication. Okay. So don't worry, they are not they have not they have never ever asked about mathematical things. But just you may it's always better to have a little bit of idea about what is point addition, what is point multiplication. Okay. Just a tiny bit of, right? Not exactly do the calculations, right? Definitely they will not ask about exact calculation because this is not maths uh, subject, okay? So remember elliptic curve is something like this kind of a curve. That of course I already explained, right? This kind of a curve. So what is mean by point addition? If you have 2 points like this in your elliptic curve, if you want to get the addition of these 2 points, right? So then you draw a line connecting these two line points, and it is going to cross your elliptic curve in another point because elliptic curves has this shape, right? So for example, if it is these 2 points, it is going to connect for somewhere here. Okay. If those 2 points are this one and this one, it is going to cross somewhere here. And point addition means if your value is P and Q, uh, when you draw a line connecting these two lines, you get R. So for any 2 points, you get something like R. If it is these two, your R is somewhere here. If it is these two, your R is somewhere here. Okay. So then this P plus Q is R. Actually, this is minus R. This is R. Don't think that we are just measuring the heights. No, there's something else going on. Actually, it's a distance between the coordinates. So just remember this, when you connect these things, what you get is minus R. So then you can find the corresponding plus R. And this length has a connection between these two heights. Connection. Okay. That real connection we are not going to look at because this is not maths topic. So anyway, that is called, if they ask about it, this is what you need to do. Just draw something like this and write down this formula. Remember, this is minus R, then this is plus R, mirror image. So then you just need to write R equal P plus Q, and this is called point addition. Okay. In case they ask, they have never ever asked. Okay. But these are mentioned in your UCSC note. Okay. UCSC note. That is why I just mentioned it. Okay. Right. So that is called point addition. So then they have mentioned another concept called point doubling also. So don't worry too much about those things. Okay. So it's an even little bit more complicated concept, but I just explained you what is point addition only. But just remember ECC algorithm use these concept like point addition, uh, point doubling and so on. Okay. Then it use another concept called scalar multiplication. All those things are mentioned in your UCSC note, but don't worry too much because those are bit of mathematical concepts. Okay, very mathematical, highly mathematical concepts, right? Just remember, if they talk about elliptic curve algorithms, so what are the related concepts? First of all, you must remember the what is elliptic curve and its shape. So we use concepts like point addition, point doubling, uh, scalar multiplication. So those are related because sometimes you get true false questions. So if they talk about these things and they mention that it's is it those are related to elliptic curve algorithm, you must say yes. Right? Scalar multiplication, point addition, point multiplication, those are related to the real elliptic curve algorithm. Okay. Right. So we are not going to look at the real algorithm. As I told you, we just mentioned some concepts related to uh, elliptic curve cryptographic algorithm or ECC. Okay. Right. Uh, so the advantage of ECC is it is stronger than RSA. So therefore, ECC can do better job than RSA uh, with smaller key size. So therefore, and also we can use ECC for both encryption, decryption, and signing just like RSA. So that is advantage. Okay. So that is why most of the time we use ECC rather than RSA. Okay. Right. So this is a comparison between RSA and ECC. You can see that ECC we can use with smaller key size, whereas RSA need larger key size to make it strong. Okay. And performance wise also, ECC is high performance when it comes to encryption compared to RSA. Okay. So the idea is ECC gives the equivalent security with smaller keys, which is good. So to get the same security for RSA, you need bigger keys and higher level of processing. So therefore, ECC is preferred. Okay, ECC is preferred. Is it clear? Right. For example, if you go for something like, say, Facebook or Gmails, you will find that mostly we use, let's say, now this one is also secure, something like this, and go to this one. Uh, Say connection is secure, more information. So see whether what algorithms they use. Um, See whether TLS, blah, 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 SHA. Sometimes they will mention. Can anyone see something like RSA or ECC? Maybe Facebook. Anyone can see? Yeah, just check. I can't find it. Okay, can't find it. Maybe somewhere here you can see what is the algorithm is. Okay. But usually, most of the time these days we use ECC. Actually, ECC has replaced most of the RSA algorithms. Okay, right. So that is uh, the second algorithm, right? ECC. The third algorithm is DSA, right? DSA. Uh, so DSA is digital signature algorithm, which is use only for digital signing. So there is a limitation. So this is the third algorithm. You can't use DSA for encryption decryption. It can be used only for digital signing. So the other two we can use for both, but this one you can use only for digital signing. So just you need to keep that in mind. Okay. So we have only discussed three algorithms. So remember, Diffie-Hellman key exchange is not a encryption decryption algorithm. It is used to transmit keys. So that we will be discussing in the next class when we look at the key exchange protocols. Okay. So therefore, Diffie-Hellman is not a asymmetric key cryptographic algorithm. Uh, it's just a key exchange protocol. Okay. So Algamal algorithm is also related to the Diffie-Hellman key exchange protocol. So therefore, don't get confused because these things are mentioned here. I just added, but actually we are going to look at these things in the next class when we look at key exchange protocols. Okay. So remember we use the factorizing of large prime numbers in some of these algorithms. Okay. Right. So this is a comparison between symmetric key cryptography and asymmetric key cryptography. So symmetric key cryptography is simple, but practical problem is since we share our key with the other party, uh, that is not very secure. Okay, that is not very secure, right? But whereas asymmetric key we can use with millions of people like Google Gmail, and also but asymmetric key cryptography is little bit slower. Okay, slower compared to symmetric key cryptography, and you need bigger key sizes also for asymmetric key cryptography. Likewise, okay, right. So quantum cryptography we will look at in the next after the break. Then we will look at the past papers. So we'll take a small break. After the break, we'll look at the past papers. Okay, right. So we'll start at 9, so now it's 9:56. We will start at, sorry, 8:56. We will start at 9:50. And we will look at the small topic, quantum cryptography, and then we'll look at the past papers. Okay, right. We'll start at 9:50. Okay, so let's continue. Right, quantum cryptography. So this is just an additional topic they have added. We are not going to look at any theoretical things or whatever. So just you need to understand that there's a new trend in uh, designing and developing a quantum computers. Right, so quantum computers, it's a reality now. For example, the Google has already uh, claimed that they have developed a quantum computer or they have made quantum computing possible, but quantum computing is not going to replace traditional computing because quantum computing is going to be used in very narrow areas only, just very specific applications only. It's not going to replace our mainstream processing. So the mainstream processing will continue to be based on logic gates like transistors and so on. But quantum computing, it's still a research area. One of the area that will be challenged with quantum computing is cryptography. Cryptography, because cryptography uh, need, if someone try to hack a particular identify a key or something, they need a lot of computational power of a specific type, lot of guessing and so on. So for that kind of things, quantum computing is really good. So therefore, one of the in a way concern is with quantum computing, these traditional algorithms are going to be challenged. So the solution itself is coming from again quantum computing, go for quantum cryptography. So that means get the solution also from the quantum computing. That is create quantum cryptographic algorithms for encryption, decryption, and so on. Okay, so that is the idea. Okay. So remember, quantum computing is based on quantum mechanics. So the quantum mechanics is alternative for traditional physics, where it's Newtonian physics. So the quantum mechanics assume that the particles have both particle and wave duality, right? Wave particle duality. So that means it's in a way particle, in a way wave. So therefore, now remember in traditional logic process, we have two states, true, false, one, zero. In quantum, when we develop a processor based on quantum mechanics, they have four states. So therefore, we call it qubits. So Q coming for four, okay, rather than bits, which is 0 or 1. Now we have qubits, which can be 0, 0, 0, 1, 1, 0, or 1, 1. So four possibilities because of that duality nature, right? Wave particle duality. So therefore, that is one of the reasons why quantum cryptography is required, because when we have four possible reasons, it makes certain calculations super fast. It's super fast. So we just look at in your syllabus, they have mentioned just one thing, that is shows algorithm. Shows algorithm, nothing else. So shows algorithm is a computational complexity algorithm. Just remember this formula in case they mention in questions. You must know that okay, this is Shor's algorithm, and Shor's algorithm is related to quantum computing, nothing else. Okay, so that algorithm is T to the Tn is it's like big O notation. We discuss in data structures and algorithms. It's complexity formula rather than algebraic formula. O, that is big O notation, ln to the power 3. Okay. So the running time or the complexity of algorithms based on the input size n is O ln n to the power 3. N is the input size. Input size. And this is the complexity. Okay, so just remember this because they have asked that I think one past paper question, write down shows algorithm. So then you need to write down this algorithm. Okay. So this is a complexity algorithm uh, related to quantum computing or quantum cryptography. Right. So that's it. It's just a tiny introduction only. So now we can move on to the past papers. Okay. Right. So the past papers every year you get about two questions from RSA and one question from uh, factorizing Euclidean algorithm. So now you should be able to do these things, right? So remember the formulas, then apply it. But just understand the scenario, whether it's encryption, decryption, or crypto, digital signing. So then identify whose key you are going to use. Okay. Right. So this is last year paper. Nimal generate two prime numbers, P equal 11 and Q equal 17. So this is little bit difficult because you start from earlier step. Okay. So during the RSA key generation process, he selected his public key as 7, public key E as 7. So remember this is encryption, decryption. So E is 7. E is 7. Together with N equal 187. Then his private key D is equal to 23. With N equal, or anyway, N is not going to be changed, 187. Okay. So you need to verify whether it's true or false. So remember the formulas. Right? C equal, let me write this because I need this all the time. C equal P to the power E mod n. Here, P equal C to the power D mod n. Mod n. Okay. So E, the real private key is D because D is not shared here. Okay. So real private key is D because N is actually part of the public key. Okay. Now what we have given, E equal give E given, N given, okay, D given, and again N given. So almost everything is given, right? Almost everything is given. But additionally, now remember we have another thing that is phi is P minus 1 into Q minus 1. Okay. And so that also we need to, because they have given you the P and, let's go to the question. So they have given you the P and Q also. Now P and Q is used for that calculation of the key. Okay, calculation of the key. Now you need to justify or connect P and Q with these values and say that these are correct. These are correct key values. This is not encryption decryption question because they have not given you plain text and ask you to verify whether you get the correct plain text back. Rather, this question is asking you to verify whether these are valid key values. Okay, right. So this is the answer basically. Uh, so remember, okay, let's get back to this. Uh, so remember we calculate 5, which is P minus 1 into Q minus 1. So once you select our P and Q, in this question P and Q are given, we need to select 5 such that it's P minus 1 into Q minus 1. So then what we need to do is that we give you 5. You need to find E into D mod 5. Now we have calculated the 5. If you have selected P and Q, you need to make sure that E into D mod 5 equal 1. Right? Right. So that's it. So now let's get back to our question. Right. So they have given E. Right? They have given E. Now we want to double check whether these values satisfy this formula. Right? E is 7. D is 23. Mod 5. 5 is P minus 1 into Q minus 1. P minus 1 is 10. 10 into Q minus 1, 60. That is 160. So 160. If this is 1, these values are correct. E and D values are correct. Okay, so that means E 7, D 23 into mod 5. 5 is P minus 1 into Q minus 1. Remember, P and Q are big prime numbers. So that is 10 into 16. That is 160. If this is 1, so these are correct. So let's see whether it's correct. Right? So 23 into 7. So here you don't need a calculator. 21 to 14 plus 2, 60, 16. 161 mod 160 is what? When 161 is divided by 160, remainder is 1. Yes, correct. So we get 1. So therefore, these are valid. And these are valid. Properly selected E and D values. That's all. Okay. So thus, these private keys or private public keys are correct. Okay. So just you need to go with the theory. So remember how you started. Find big prime numbers P and Q. Then make sure you select 5, which is P minus 1 into Q minus 1. So then you select E and D such that E into D mod 5 is 1. That step they have checked. So this is not encryption, decryption. This is just to check whether these keys are correct. Okay. Right. Right. So this one is the traditional question. Okay, this one is a traditional question. Let me erase the other stuff. Right. So this is let's just check first whether it's encryption, decryption, or digital signing. And where is Kamal? Where is Nimal? Kamal has an RSA key this and private key this. Suppose Nimal encrypt plain text are Nimal encrypt, and this is Kamal. Okay. So this is encryption. This is decryption. So that means you need to use Kamal's keys. Straight away you know that you need to use Kamal's keys. So that means E equal 7, N equal 33, public key is given to Nimal. And private key D equal 3 and N equal 33. Okay. Right. So the correct keys are given because Kamal's keys you need to use. In this question, only Kamal's keys are given. Suppose Nimal encrypt the plain text message 5. So P, M is P, 5. To Kamal, then Kamal receives ciphertext 14. So you need to verify whether is it really 14. Right. So that is C equal P to the power E mod n. 5 to the power E 7. This is part of the public key. Mod n is 33. So calculate 5 to the power 7. You can use, you don't need to use a calculator, but I will do it, make it fast. 5 to the power 7. That is this mod 33. Mod 33. You can divide it by 33 and you don't need a calculator for that. And answer is 14. Yes, so the ciphertext is 14, correct? Right. So you need to say true and you need to do this calculation, draw this diagram, right? Whose keys are used and get the answer. Okay. Simple as that. Is it clear? Now all the questions are like that. Very easy. So this one is uh, digital signing. So then you need to use the formulas in the reverse order. Right? Use formulas in the reverse order. Okay. Kamal has RSA public key and blah blah blah. Kamal sign a plain text. Now Kamal sign a plain text. So Nimal verify. Sign verify. So keys are generated by Kamal. And Kamal has a private key. Kamal has RSA public key. Public key is used here. E equals 7, N equal 33. Uh, private key is used here. D equal 3, N equal 33. Suppose Kamal sign a plain text 7. So that is P equals 7 to Nimal. Then Nimal receives the signature S equal 13. And you need to double check whether S equal 13 is correct. Right? Of course, it must be verified to 7. Okay. Right. So now you need to use this formula because this is encryption decryption. Signing means this comes here. But rather than P, we call it C equal P to the power D mod n. P is 7 to the power D mod 33. So 7 to the power 3 mod 33. 7 to the power 3 mod 33. That is the sign. The sign is 13. Yes, the question says 13. And yes, we get 13. So therefore answer is true. Okay, answer is true. Okay, 7 to the power 3 mod 33. So you need to do it with understanding what you are doing. Okay. Right. So this is the same year. Uh, elliptic curve cryptography provides the same level of security with smaller key sizes compared to RSA. True or false? Answer is what? Answer is yes. So that is the whole reason why we are using it. Elliptic curve cryptography provides the same security as RSA with smaller key size and faster processing. Okay, faster processing. So that is why ECC is preferred. It doesn't mean that RSA is bad. Simply ECC is better. Okay, ECC is better. So elliptic curve cryptography achieves the same level of security with RSA with significantly smaller key sizes due to the mathematical complexity of the elliptic curve discrete logarithm problem. In simple terms, solving elliptic curve DLP is computationally much more difficult than solving the integer factorizing problem. So remember, integer factorizing is used in RSA. Right? So, but in elliptic curve, we use that doubling and blah, blah, blah. Okay, which are much more complicated calculations. So therefore, it gives you better strength. Okay? Better strength. Right. So now you should be able to do this one. Okay. Because all the steps are given here. We did this question, right? Yeah, we did this question. So with this one, still we are in 2025. I told you this is where you get most of the questions. Which cryptographic function is not used for user authentication? So remember, user authentication is for what? Is digital signing. Digital signing is done for user authentication. So remember, ECC and RSA can be used for both encryption, decryption, and digital signing. Remember, we discussed about AES. AES is a symmetric cryptography. We have already discussed AES. Okay, so therefore AES can't be used for authentication. AES just for encryption, decryption. Right? Symmetric key cryptography can't be used for digital signing or authentication. So therefore answer is uh, AES. Okay, AES. So So bcrypt is actually hash function. If you don't know about bcrypt, still it doesn't matter because you know that definitely AES is wrong. Right? AES is wrong. Okay, because AES is uh, symmetric key cryptography. Symmetric key cryptography can't be used for authentication. Okay, or digital sign. Right. So what about the next question? Still we are in 2024. Lot of questions. Okay, lot of questions. Which cryptographic algorithm is commonly used for encryption, digital signature, and key exchange? Right. So which one is used for encryption? Of course, for encryption you can use RSA and ECC, elliptic curve cryptography. Okay. Uh, Digital signing also you can use both because both we can use RSA and ECC for both. And as I told you, key exchange protocol is Diffie-Hellman. Anyway, we are going to do Diffie-Hellman in the next class. That is your next topic. Right? So AES used for that is AES is also symmetric key. ECC for digital signing. Uh, Diffie-Hellman is for key exchange. RSA used for encryption. Actually, I don't know why they have not taken ECC because ECC also can be used for encryption and digital signing. So examiner has taken only RSA, but in reality, it can be RSA or ECC. This can't be used, this can't be used. These are for two different purposes. But examiner has taken only RSA, I don't know. Okay, so let's check with the, because ECC can be used for both. I think your note also mentioned like that. Okay, shall we check with ChatGPT? Because your note also says like that, right? By the way, now this is done, right? Yeah, this is done. List down usages of ECC algorithm. So usually you should ask open questions. Like public, you can see digital signature, right? Public key encryption, digital signature. You can use for key exchange also, right? Support. Yeah, there's a variation of Diffie-Hellman for elliptic curve, but anyway, it's not major thing. So authentication is because it's digital signing, okay? So many usages, but so that you can see definitely ECC is also used for digital signing. So it says which one can be used for digital signing. Examiner has mentioned only one, but for me, both one and four are correct. Okay. Right. Still, we are in 2024. What is the primary disadvantage of asymmetric key cryptography? So the primary disadvantage of asymmetric key cryptography is what? It's slower compared to symmetric key. Right? Slower. And because these algorithms are much complicated than symmetric key cryptography algorithms. Right? And also you need large keys compared to symmetric key cryptographic keys. Okay. So slow encryption process, yes. Require secure channel for key exchange, no. Because public key, we keep the private key with us. You need secure key exchange info when we use symmetric key because we are sharing our key with secret with the sender. So how do we send that secret to the sender? Still we have not encrypted. But here we are only sharing the public key. Public key is useless for decryption. So there is no key distribution problem for asymmetric key. Key distribution problem is mainly for symmetric key. So there's no brute force attack, okay, for modern ECC and so on. So slow encryption process, okay, right. So now these are just say similar questions, okay, just they change the numbers and so on. So you should be able to do this, okay. You should be able to do it by yourself. This is again digital signing, okay. No, just like that, starting with the P and Q. Just double check whether these keys are correct. Like same question, right? Just numbers are different. Okay. This is encryption, decryption, just verify. Okay. So this is 2023, same type of questions. Okay. This is digital signing question, same type of question. Right. Just you make sure you use the correct formulas. And GCD question, right? We already did, we have done that. Right. So then some theory questions, 2023 still. Okay. Which encryption algorithm is considered insecure and is no longer recommended for general use? Okay, general use. So remember, RSA has no issue, right? Just ECC is better than RSA, right? Still, we can use RSA. So therefore, no issue with RSA. Anyway, Diffelman is for key transportation. So therefore, I don't take that as answer because it is not. There's nothing called it is insecure. It is used for different purpose. And of course, AES is no issue, right? Because this is a symmetric key. Remember, DES we discussed. Now you need to remember the symmetric key algorithm because we have already done. There we discussed that DES is vulnerable. So that is why we discuss about triple DES. Right? Because DES is vulnerable, we use triple DES. So don't use DES. Or if you really want DES, at least go for triple DES. Or you go for AES. So therefore, which one is vulnerable? This one. Of course, this question is mixing both symmetric and asymmetric key exchange, everything together. Okay, because now we have done those things. The answer is DES from our previous topic. Okay. Right. So this is same similar type of questions. Okay. Right. So I'm not going to do these questions. Uh, right. So you can see if all 3 years, it's like same mold, different questions. Okay. Right. So GCD question. And then maybe one or two theory questions. Which of the following algorithm is used to create digital signatures? So digital signing. Remember digital signing, you can't use symmetric key. Okay. So DES you can't use. Triple DES you can't use because all are symmetric. Ecliptic curve cryptography we can use. AES is also symmetric. AES is strong, but it's symmetric. So digital signing, you can use RSA and ECC. And the third one we discussed that can be used only for digital signing, but not for uh, encryption, decryption. What is the third one we discussed? The third algorithm? Uh, yeah, DSA, right? Digital signature algorithm also, but that can't be used for encryption, decryption. Okay. So in this case, this can be used, right? DES can be, sorry, DES can be used. Sorry. DES is digital encryption standard, right? Yes, DES can be used. But I don't know whether examiner take ECC because last paper also examiner did not take ECC, right? Only RSA. Uh, but I don't know. For me, both ECC and DES is correct. Okay. Or DES is now this time AES is taken. Sorry, not DES, right? Digital Sorry, I really mess it. So this is called what? Uh, digital, not DES. This is DSS, right? Sorry, DSA of compatibility. So digital signature algorithm is what? DSA, not DES. DES is that vulnerable one. So, yeah. So DSA can be used, ecliptic curve can be used, RSA can be used. Okay. ඔක්කොම පැටලලා තියෙන අකුරෙන් දෙකකින් මාරු වෙන්නේ. So therefore, DES cannot be used. That is the symmetric key vulnerable guy. So therefore, it's a ECC. Right. On එතනදී ECC අරන් තියෙනවා. අර කලින් paper එකේ ECC ගත්තේ නෑ හැබැයි digital signing එකට. හරි. So therefore, ECC, elliptic curve cryptography. Okay. Right. So that's it. Right. So you can do some more past papers, right? I just cover 3 years. So you can cover at least another 3 years. Okay. But these questions are very straightforward, same mode. Okay. Right. So we stop at this point, right? Thank you.